Kia ora tātou, welcome to this video on Le Chatelier's principle, where we will introduce the principle and look at the factors that are relevant for our topic this year. So Le Chatelier's principle, if we first of all take, if we take the reaction here, we've got an equilibrium reaction. So I've made this slightly more complicated than what we've been looking at previously. So we've got A plus 2B goes into C and D, and then when this reaction occurs in the forward direction, we release 100 kilojoules of energy. So what does Le Chatelier's principle say? So it is, if a change is imposed on a system, and we'll look at what these changes can be, then and the system is at equilibrium, then the system will respond to minimize the change placed on it. So we don't need to be able to quote Le Chatelier's principle exactly, like this isn't the exact proper quote from that principle, but we do need to be able to apply the ideas behind it and sort of reference it. In the next videos I'll show you how we would write exam answers as well. But this video we're just introducing the factors that can be imposed on a system to force it to change. So the first thing that we can change about this system is we could change the concentration of A, for example. So if we had a system that was concentration. So if these were all in an aqueous form, and there was like 5 mil of these reactants and products in a solution, if we just added some of A without changing the volume, then that would be changing the concentration. And so because we've added some A, we know that the equilibrium constant, so when this equilibrium is at when this reaction is at equilibrium, there would be a particular value for Kc. So it could be that Kc is equal to 1, and so normally, if that reaction was at equilibrium, but if we increase the concentration of A, then we're going to be dividing this value by a greater number, which would mean that we're going to get a value that's lower than 1. So let's say maybe it turns into 0.8. So what's going to need to happen is that this reaction is going to need to do something in order to re-establish that equilibrium, to get Kc back to 1, because at any temperature, the equilibrium constant will always be that value. That's the whole point of it being a constant. It stays the same. So yeah, so in order to minimize the change of increasing the concentration of a reactant, the reaction will actually start to turn some of that reactant and some of that B into C and D, so that would increase the value of the denominator, and then we would get our equilibrium back to our reaction back to equilibrium. So we can change the concentration in order to change the position of the equilibrium. We could also change the pressure. And so this will be if we've got different numbers of moles on each side of the equation. So in this case, see how we've got 3 different particles? We've got 2 of B, and we've got 1 of A on the left-hand side, and we've got 1 of C and 1 of D on the right-hand side. So this means that if we were to increase the pressure of a system, so let's say we had a volume that was that big and then we reduced it to that much, if there were 10 particles in there, when we reduce it down to a smaller volume, in order to keep the equilibrium constant the same, it's going to have to reduce the number of particles in the system. And so to do that, it would create more of C and D, because that's going from 3 particles to 2 particles. So it might go down to like 8 particles, and that will keep the equilibrium constant the same. It's much harder, well, I find it much harder to show that using the equilibrium expression, so that from my perspective is just learning the concept. And then the final thing that we can learn how to change will be heat. So with this, we've seen that this will release 100 kilojoules of energy when we go in the forward direction per mole of the reactants used. So we can actually rewrite this reaction as being plus heat. And so if we increase heat, the heat of the system, so if this was occurring at 20 degrees Celsius, if we increase that to like 30 degrees Celsius, then we're effectively adding 10 degrees of heat. And so if we're adding something on the right hand side, it's similar to what we were doing with the concentration there. If we increase this, then in order to reduce the heat, to minimize the change imposed on the system, we need to go back in the opposite direction. And so that's the only thing that would actually change the equilibrium constant. So if you remember from the equilibrium constant videos, the equilibrium constant is a constant at for a particular reaction at a particular temperature. So when we change the temperature of the equilibrium, we will actually change the equilibrium constant. So in the next videos, we will go into depth about these three changes that can be imposed on a system. This video is just our introduction to Le Chatelier's principle. So there you go. Good luck with pronouncing it. See if you can do some research on him. It could be useful for the 2.3 internal as well, these concepts. So I'll see you for the next videos where we'll go over these. Thanks.